Wonderful. So it's really nice to see everyone. This is a great time to talk a little bit about the work that you've done in collaboration with Caltech. These projects have been a lot of fun actually to oversee. They have to do with quantum chess, and it's great that we have Chris Cantwell, the creator of quantum chess, here with us. And we have three different presentations actually. So Dylan, Robert, and Karis will be discussing some of the work they've done over the past couple of months. And I think we can start, I don't know, maybe we start with Robert. Are you okay with that? And you should have access to sharing screen. If you don't, let me know.
Okay, yeah, I think I can share screen. Okay.
Perfect.
Okay. You guys can see that, right? Okay.
I think we can see also the full presenter mode.
Oh, here. Let me change something. That's weird.
Not a problem.
Okay, I think I'm sharing this second desktop, so I don't think.
There we go. Yeah.
Okay.
Beautiful.
Perfect. Okay, so hello. Over the past several weeks, Dylan and I have been working to create a program that can play quantum chess and specifically evaluate certain positions. And so the AI of a turn-based game like chess often includes multiple different components that can be split up and simplified into these three main abilities. So of these three, so first, the ability to look into future positions and see possible outcomes. Secondly, to evaluate those outcomes numerically. And then third, to use those outcomes to come back to the original position and to make a move. And so of these three abilities, generally the hardest one to program is the second, evaluation of outcomes. And so what we're seeing in this diagram is pretty much, let me turn on my laser pointer, a representation of an original position being split up into possible moves, given evaluations, and then coming back into this original position. We'll see that a little bit more later on. So to briefly explain what an evaluation function is, it's to assign, the purpose is to assign a numeric value, either positive or negative. And in the case of chess, the white will usually be positive while black is negative, although I guess you could flip that, to assign numeric values to chess positions. And so you could say that a position that has a value of 5 is generally, it's pretty good for white, whereas a position that has a value of -50 could be very good for black. And so that is the numeric system that can be easily understood by computers. So that's the point of the evaluation. And if you play chess, and honestly, even if you don't, you can intuit that having pieces, especially strong ones like the queen and rook, is generally a good thing, especially when your opponent doesn't have such pieces. And so a good initial approach to creating an evaluation function can be to just tally up pieces based on, the queen can be worth this much, the rook is worth this much, and if I have more pieces than my opponent, then I can say, then this is a good position. And generally, this is an okay start to an evaluation function. But the problem with this is that chess is a very complicated game. And if we look at this position over here, we can see that the white knight, it can possibly travel to 8 different squares, while these 2 black knights, while they have the double the value of the single white knight, they can actually only reach 5 different squares. And so you can see that positioning, as well as the time of the game, middle game, end game, those are very nuanced things that come into play in an evaluation that can be seen by humans, but is very hard for a computer to see. And so that is where this comes into play on the right. And this is called Stockfish. And this is a visual representation of some of the calculations that it does when you hand it a position. And modern chess engines have become very good at looking at these complicated positions. And so Dylan and I decided that rather than trying to create our own function that looks something like this for quantum chess, might as well simplify the problem. And so what we did is use something called a library in Python, the Stockfish library. And what that is in Python and other programming languages, you can access code that was written by other people and borrow it and implement it into your own work. And so what we took is a program that is trained to look at regular chess positions, not quantum chess positions, and give an evaluation, and then use those evaluations and apply them to quantum chess. And so the way we did this is, well, this is what it looks like to play quantum chess through the command line or through Python. And this is a quantum chess board here. And so we can see that a pawn, it's a bit hard to understand, but a pawn has moved from E2 to E4, while the black knight has made a split move from G8 to both F6 and H6. And these numbers don't represent the pieces, rather like, pawns, kings, and queens, but they actually represent the probability of that piece actually being there in the given board. And so we can see that these two knights, because they came originally from one split knight, they have a probability of 50%. And so down here, we see there are two samples, samples 0 and sample 1. And the first sample represents a position where this knight moved to F6, while the other sample represents, and these positions are classical chess positions, meaning not quantum chess positions. And the other sample represents a position where the knight actually moved to H6. And so you can see that a quantum chessboard can actually be represented as a number of different classical chess positions, which can be thrown into Stockfish. And so that's what we did. By using Stockfish, we got an evaluation, and then based on those probabilities, we made a weighted average based on those evaluations that could be applied to the full quantum chess position. And so that was our first primitive approach. But there is a slight problem with this, and it's that Stockfish, when handed these quantum positions, can't see quantum moves in the future, or they can't see moves that would only exist in certain quantum positions. And so in this diagram, we see that this knight only has a 50% probability of it being there, as does this pawn. And so this bishop, while Stockfish would think there's pieces blocking it, this bishop actually could possibly be able to grab this pawn. And so this is just an example of how Stockfish is actually missing a lot of moves because it can't see quantum moves. And so the solution and this is where Dylan and I branched off and started working on different things. So my solution was to use something called Minimax. And so to explain what Minimax is, the name or the idea is actually hidden within the name, Mini and Max. And so it's an algorithm developed for two-player games where one player is the maximizer, in this case white, and the other player is the minimizer. And so players are generally trying to make moves that are the best based on these evaluations. I'll explain that in a moment. And you assume that the other player is also going to make smart moves. And so what we see here, this is a bit abstract, but this circle called a node basically represents a chess position. And because it's white, it means that it's white's turn to move. And you can assume that these branches are moves. So this is white's move, and it becomes a different position. This time it's black's turn to move. Then black moves, and then white. It becomes white's position once again. Now, what these numbers represent on the bottom are the Stockfish evaluations. So you could say that if you pass this quantum position into Stockfish, the method that we created, then it would give an average of about -1. And so, as I mentioned, white is the maximizing player. And so if you imagine this as a game state, looking at two different possible boards, white will choose this move. It'll choose this board. And so you can say that this white node should have the value of 3, because if you ever get to this position, white will choose to move into this line, right? And so if you look at a completed tree, you can see that white will continue making the solid moves that maximize their value, while when it's black's turn, they'll pick the lowest move, the minimizer. So they'll pick 3. Ultimately, white gets the final decision, and they choose the highest value they can, and that's number 3. And so what just happened? What does number 3 mean? Basically, what's happened is we've split this single position into 8 different positions by looking 1, 2, 3 moves ahead. And by the way, that's called a depth of 3. And so we've looked at those 8 positions and determined that what will happen is white will make this move, then black will make this move, and then white will make this move. And so essentially, this is the future position of this. And we can go ahead and say that this has a value of 3. That's the general idea of minimax. And so why are we applying minimax to, we've already started using Stockfish. So why do we need to use minimax as well? And so the purpose is to be able to see future quantum moves that Stockfish could not see. And so if we look at this diagram, we can see that there are many possible chess positions coming from a single board after making a certain move. And this includes different quantum positions. And so that's what minimax is looking at, all of these positions. And you can see that this tree obviously looks a lot more complicated than this one. And that's because this tree has something called a branching factor of 2, which means that for each node, there are 2 different possible game states that it can go to, right? And so at a depth of 3 with branching factor of 2, then there are only 8 positions. It's a fairly clean node, or a fairly clean tree. But with chess, the branching factor is about 35. And in quantum chess, we don't even know. It's definitely higher, but we're not quite sure, I don't think. But you can see that the branching of something with a branching factor of 35 would become quite a bit larger than our original, very simplified minimax tree. And so there is another problem with this approach. And it's that minimax, and we're no longer missing any moves. We're no longer not seeing quantum moves. The problem is that we're seeing everything. And that's just too much for a computer, especially my computer. It's a Mac. And so there are different methods of speeding up this process, or minimax. Not so much speeding up, but actually looking at fewer positions. And so one method is called pruning. I can explain it in questions. I'm not sure if I have the time to go into it now, but what I mainly looked into was limiting the branching factor of the game, or of the quantum game. And so here was my approach. The reason why minimax is, or the reason why running minimax like this is quite slow is because for each position, you have to look at 35 more positions. And for each of those positions, you have to keep looking even further. And so basically, I created minimax 5 and then later minimax 1. And the idea is in the name once again. It's to limit the branching factor of the game to 5. And so minimax 5 runs a Stockfish evaluation, which the Stockfish evaluation is much faster than continuing to run minimax because Stockfish itself has become very optimized. We run our Stockfish evaluation on the position and find the 5 most promising moves. And from those 5, we run minimax 5 once again. And so what we're doing is instead of looking at 50 moves per position, we only look at 5. And ideally, we're not missing out on the positions where you're making bad moves, because hopefully those positions, they wouldn't happen because you're looking for the best moves possible. And so I also created minimax 1 as well. And so that is no longer really a search tree, but rather a bunch of lines, or a game line with different positions within it. So here's some of the data from these different models. And this is minimax, baseline minimax. And you can see we could only run to depth 2. And that's because if I ran anything further, it would take hours. And it's unreasonable. And while 2 is a very low depth, which it does look quite weak, the Stockfish evaluation itself that I was using was running on depth 10. So you could see that all in all, it's running on depth 12, but only the first 2 moves can register quantum moves, right? So all in all, it's about depth 12 because the purpose of the minimax here is to see some quantum moves in the future. And so we can only see 2 quantum moves into the future. And so you'll also see that there is timing and function calls. And the reason I include the function calls, which basically means how many times the minimax function was called at the given depth, is that it's often unreliable to look at just timing, especially because it's very heavily dependent on operating systems, background things your computer is running, and even the temperature outside. And so sometimes it's easier, or it's more helpful to look at the amount of times the function has been called, although it's easiest to visualize using time. So I ended up including both. And so this is called alpha beta pruning. This is minimax with alpha beta pruning. That is just a method of pruning that I use. That is basically an optimization on minimax. And you can see that we were able to get to a higher depth, but that still took a long time. This is an improvement, but it's still not quite usable. And so minimax 5, which is once again an improvement, is still a bit too slow. But you can see that the function calls have been reduced drastically. And that's because we're only running minimax on 5 positions per, per passed position. And then so finally, minimax 1 is pretty much my final product. It can look into depth 8 at a relatively okay speed compared to the other programs. And overall, that if you add the depth from Stockfish, it's overall about depth of 18. And so you can see that the function calls mirror the depth. And that's because, once again, we're no longer looking at a tree, but rather a line of events. And this is pretty much my final product for the board evaluation. So yeah, thank you.
Thank you. That's awesome. Okay, so I feel like I have some questions, but any questions from anyone else on the call?
Yeah. What position were you starting with for those minimax tests?
So those positions were actually this position right here.
Okay.
Yeah, because every time I ran the program, it took a couple minutes, especially on the lower, like the first few models. I didn't have time to try it on mid game, end game. Although I would be curious to. Yeah.
Yeah, I'm curious what it would do on like a more complex position like Kiwi Pete. Have you heard of the Kiwi Pete position?
I haven't, no.
You should Google it. It's
okay.
So I did some perf T testing just to estimate the branching factor of quantum chess and came up with an average branching factor of like 108. One of the positions I used was Kiwi Pete. It's like a kind of a contrived board position that has one of the largest branching factors you can get in chess with a lot of different pieces on the board. So.
Mm-hmm. Okay, yeah, I'll definitely look into that. Yeah.
Any other questions?
Does the Stockfish library, is that something then you contribute to? So you're pulling code that other people have created? Like, would you share your code with that, like open source, or how does that piece of it work? Because it seems like really smart to be able to utilize chunks of it that have already been created, so you're not starting from scratch.
Yeah, so I think specifically Stockfish, I'm not sure who created it, but I think it's from some sort of large organization. But in general, you can post your code to different websites, GitHub, Stack Overflow. I mean, coding or programming, it's a pretty large community of people that like to share information so that, you don't waste time programming what other people have done. So yeah.
I assume also that whatever we create, at least maybe for something like this, a project, one of the original ones, Mitch, is, I don't know if it's going to be open source right away, right? The evaluation for quantum chess, because Stockfish is already kind of, there's open versions, right? Which Dylan and Robert used. But yeah, I think what this team is developing is something that will be used for educational purposes, to have a quantum chess AI that can then help with like puzzle creation for educational purposes and other things as well.
I have a quick question. So I know we worked together for a long time, but we kind of like split off after like a fair amount of time. The first one is, how did you end up dealing with like the illegal Fen position put into Stockfish? What ended up happening there?
So yeah, basically it's during the minimax function itself and during my like method that samples into Stockfish, there are a bunch of different checks to see whether a king has moved into check, which crashes the engine, or whether there's no king on the board. And so for checking for a king on the board, I used a pretty like primitive method, which actually seems fairly effective. It's that the string itself, I just searched for whether there's a K or lowercase or a capital K, because that means that there is a king on the board for either side. And so if there was no K, then generally that meant, you know, there was no king. But I was careful to, I was careful that, because the fen string itself actually contains a K and a lowercase k for castling rights, but I had to make sure that wasn't included in the check. So.
Also,
yeah, go ahead.
I also had one other question. So so were you able to test it at all, or in like actual gameplay, or not yet?
I tested it in positions where I knew there was no king, or if there was something in check. And mainly the testing came when I was trying to run Minimax, and the engine would stop working. And that was when I knew there was something wrong. But I'm pretty sure that at least for positions that involve the king, whether, you know, the king's in check or there's no king, that those positions aren't a problem. Although, as we've discussed, we haven't created the perfect evaluation method for those positions without a king. So, yeah.
Okay, so Robert, just one question from me. So the function calls went down quite a bit, but I still see, you know, a computer works at the level of like microseconds or milliseconds or something like that, right? So you should be able to do like thousands of function calls like in 1 second. So what's happening here when it takes like a minute, right, to do, I don't know, 50 or something?
Yeah, so for one thing, I was thinking of including as well the number of times Stockfish itself was called, because in the sample evaluation method that we use, it needs to call Stockfish. And I use Stockfish, as I mentioned, at depth 10, which is fairly quick, but you know, it's not instantaneous. And so it does end up calling Stockfish quite often, especially in the later, especially in Minimax 1, where there's very few function calls, but it still takes some time. And that's because I'm still evaluating the positions using Stockfish and then choosing the correct path. And so in the end, it's not, you know, super fast.
I would be very interested to see what would happen if you had Stockfish at like 5 or 6, honestly, right? And then use Minimax 5, because that could be like the answer, you know, something where you can start really, you know, have a good quantum chess AI that is not very, it doesn't take very long. Because yeah.
Yeah, I agree.
Otherwise, you're playing more classical chess than quantum chess. So, but it's easy, I assume, to like change these parameters, right? It's like,
oh yeah.
Cool.
Yeah.
Perfect, awesome. Okay, thank you. All right, let's move on to Dylan.
Pull the presentation. Here. Can you all hear me good? Yeah, nice. Can you see the presentation? All right, so I did a very similar project to Robert. We did the same thing, but we took some slight differences in our approaches, which I'll talk about a little bit, and also give some similar background to what Robert did. So what is quantum chess? As Robert's already explained, it's a lot like classical chess, except you can create certain split moves, and your king can also be partially captured too. And there's a lot of slight variations that make it different from chess, where you can split the board into different pieces. And also you can create a whole bunch of different moves that you wouldn't be able to do in classical chess. So the goal of this entire project was first to create something that could evaluate the quantum chess position. And second, find a set of moves to bring me to that optimal position, which is what we ultimately ended up using the Minimax for. So there was a lot of challenges with this project, especially for me. I think Robert was actually able to do a lot better in this project than me. But I think the main one I had was an extreme time limitation, because I ended up going on vacation for a lot of it. So I was trying to really simplify the problem as much as possible. Originally, I was thinking in my head, I'm going to do like this AlphaZero super advanced AI that cannot be beat. But that didn't end up turning out what happened because like time limitations always stop you. So I ended up trying to actually make it as bare bones as possible, use programs that people have already created, and really try and make it as simple and be ultimately as lazy as possible and make it an easier problem to solve. And the other problem we had was compute limitations. And the third and final problem we had was a little understanding of the strategy. So I'm not like an expert quantum chess player myself, so I really had to rely on the computer to figure out how to play the game for me, which also made the game and solution to this AI problem quite challenging. So the way I saw it was that there was two main approaches to any chess engine. The first one was the AlphaZero, which I talked a little bit about earlier, and the second one was the Stockfish. So a little bit about AlphaZero. AlphaZero is the best solution to classical chess. What it does is that it takes a super advanced AI that has millions of different parameters, and looks at a position and then evaluates it, and it'll search through a few thousand moves, which really is not that many moves. But what it really focuses on is getting a really good evaluation of the board. It has a really good positional understanding, and it can play really, really well and beat any other engine or any other player. The problem is that it's really complex from a data science point of view because it has self-play, which comes with a whole lot of problems. And also it is really reliant on deep neural networks, which require lots of training and also lots of computation. So ultimately I decided against this because it has a really high level of complexity, especially when you're dealing with like neural networks, really complicated. And also I just didn't have time to program something so complicated with such advanced parameters. The next solution was Stockfish. There's certain positives and certain negatives of Stockfish is that it uses a manual rule set. So this is good in many ways because it doesn't require a lot of computation. It uses lots of like, if your knight is here, +1, or if it's here, then -1. So it uses lots of ands and ors, and it essentially uses a lot of user input. People program it very specifically. It's not some robot that does it all for you. Stockfish solution is very reliant on the program to understand the game and ultimately program the rules that create the evaluation. It also uses, as Robert talked about a little, it uses the opening, the mid game, and the end game, and combines and uses 3 different evaluations in order to combine it into one simple evaluation. But because it's using these simple rules, it's super easy to compute, especially versus like a neural network solution. So I ultimately decided on using a solution like me and Robert decided on, a solution that's really similar to chess, because we didn't have time to like program our own thing really. We really had to rely on someone else. Like to program something like AlphaZero or a chess engine, it could take like 4 or 5 PhDs, years to program. So we needed to do something that already existed to a certain extent. So we could take advantage of that and really simplify the problem. So the first thing we did was take the board states in order to evaluate the thing. As Robert talked about, he showed you some of the samples and how we can sample the different states, right? And we can get a probability for each state. So we can have one board that has a 50% probability, another board that has 25% probability. So what we do to evaluate the board of Stockfish is we take each board, right? And let's say we evaluate it and we're up 3 pawns. So that'd be +3. And then you multiply it by its probability, let's say times 0.5, and you get 1.5. And then you have another board state that has a probability of 25% or 0.25, and you multiply by -1 pawn. And then you add that to the sum. And then you can just keep iterating through the sets. Okay, so as Robert, I'm gonna kind of like not spend too much time on this part because Robert talked about a lot in his. It's the minimax, where the black will take the min and then white will take the max, and then you search down the tree. Robert did a very good job of explaining it. I don't think I could do a better job, so I'll try and glance over that. So as he's talked about, chess is kind of a similar minimax to tic-tac-toe. except for we're using the position evaluations for the chessboard, and we're using that with Stockfish and the weighted averages as we done earlier. So now I'm actually going to take a quick look at the code and kind of explain what happened and what my results are. So as you can see here, it ended up being a lot of code and a lot of like different approaches that I tried. Initially, I started with this, which is what the quantum chess team gave me, which is something that creates a quantum chess game. So I can essentially get possible moves. I can get legal moves. I can get the probability boards and also like do certain moves and actually see what the board looks like. So I'm going to give you an example of the probability boards that Robert showed you earlier. That's what this code up here allows you to do. It allows you essentially create the quantum chess game in Python. What I did with this was then I had to create a list of functions to help me with my minimax. The first thing I did was I brought in Stockfish. So I used the Stockfish and I gave it a really low time limit so I could focus on the quantum chess moves. And I also had to use a list of wrappers and to allow me to convert one type of board to another type of board, which is actually where I spent a lot of my time. And then after that, I started creating the minimax. And yeah, and you can see right here is an example game that was played out. Sadly, it didn't get played out at the end because I wasn't actually able to create an algorithm that could work without failing. For some reason, after a ton of moves, it decided that it couldn't find any more legal moves. Instead of trying to find like workarounds to the legal move problem, I essentially said that I'd try it and try putting it into the Stockfish engine. And if it didn't work in the Stockfish engine, I wouldn't allow my minimax to make that move. So I simply said, if the Stockfish can't handle it, then don't make that move, which works somewhat effectively, but isn't perfect. So overall, I got a game that was pretty effective, but not perfect. And then ultimately had an error at the end because it came to a position where I had a problem with some set of illegal moves. All right, that's all. Thank you.
Great, thank you. By the way, for both of you, did you ever see the AI make quantum moves?
Yes. I can actually show you here. I'll share my screen so you can see the game. Yeah, let's go down. I think this is the quantum game. This may be the classical game that I tried to play with it. I think that's the classical game. Maybe it's down here. Yeah, right here. So you can see it playing. So it does a lot of split knight moves. The split knight is a very popular move, but then the position collapses pretty quickly because it allows you to take up a lot of the board when you split the knight. So actually a lot of the openings I saw actually used the split knight move. But yeah.
That's cool. Nice. Robert, did you also see some of that?
Yeah, I did sometimes because the worry was that it wouldn't make quantum moves, but thankfully sometimes it would see it was the right move. And
again, like for either of yours approaches, if you didn't have the minimax in there and you just had the Stockfish, it wouldn't be doing anything but just really good classical moves, right?
Yeah.
Okay, I see. Cool. All right, Karis. Oh, I'm sorry. Mitch,
I was just going to ask if either of you will play chess differently now, having had this experience when you're just playing regular chess.
Honestly, not sure how much more chess I want to play after this.
Yeah, I'm trying to think of how that would affect my gameplay in chess. Well, I mean, chess is also kind of like a probabilistic game too. Like you can't predict everything that's going to happen. And kind of learned that lesson here is that some things are, there's just also some randomness in normal chess too, where you can't predict every possible move. So you just got to make the best move you can.
Just thinking like three moves ahead, but knowing that your opponent could throw that off quickly. It would be nice to have a pocket computer that would help you with your moves, you know, like cheating on poker or something like that. I'm sure that's coming.
Yeah. One thing I didn't know was that the branching factor was 35. I knew it was like a lot of different moves you'd have to calculate, but I didn't quite realize that, you know, for a human, that's a lot of things to think about. But thankfully in chess, you know, you don't have to look at all the moves. A lot of the moves aren't good, but you know, yeah.
I love the idea of the hybrid approach that you both took, right? Which is a weighted average between a really amazing classical AI and then an allowance for quantum moves to happen, and then to use like what we use in quantum physics, which is the expectation value in that state, right? You know, the quantum state of the board. And there is even like a lever you can pull, like, you know, to go more towards like a great classical chess player that is playing quantum chess, right? But still has knowledge and experience with the quantum moves, versus a more probabilistic and more quantum chess player can go deeper with the quantum moves, but may not have this at every, you know, classical board state does not go as deeply, right? Yeah, Dylan.
Yeah, I was trying to make something that really focused on the quantum depth, but the problem is like Stockfish is just such a good algorithm and people put so much time into it. It really has like a massive advantage over what we'd be able to make by ourselves for quantum chess. So it's just super, super powerful. So I tried to use a lot of that, but I also tried to do as much quantum as possible, because then you're missing like the quantum part of the game, and it kind of became like a difficult balance.
Yeah, it'll be one of the final parts for this, at least for me. I would like to know one day if the very best quantum chess AI, say a year from now that we have, will decide to just play like quantum moves itself, not just in response to quantum moves from a weaker player, but will just say like, no, as you said, the knight, splitting the knight, right? Because, you know, one of the principles of chess is to try to occupy the center and control the center, right? And to have your pieces have access to many different positions, right? Control many different positions. And with quantum moves, by splitting, you can have this, both because, you know, say splitting your knight, you can have many more positions in one turn that the knight probabilistically, right, is could attack, right, or control. But also because, you know, something else that's really cool about quantum chess is that the pieces can guard themselves, right? Because you don't know where the knight may be when you split it. If you split it in the right way, it could be guarding itself. So the opponent may not want to attack this position, right? Because like if I made a mistake and the knight wasn't there when I attacked, then the knight is there to attack me now. So I think it's going to be really cool to see where, actually, yeah, one of my last questions is, do you plan to continue to see this incorporated? Because you're also part of this larger group, right? You know, with some of the top minds, including also of the deep mind, right? You know, persuasion, working on this with you guys.
Yeah, definitely. I definitely want to like implement it and maybe someday do like the AlphaZero approach, which is like the gold standard of like chess engine. I think that'd be really cool if I had more time.
Very cool. Okay. All right, Karis.
Hi, okay. If it looks like my eyes are weird, it's because I've got dual screens, so I'm kind of looking up but looking down at the same time. So I am, yeah. So, okay, let me share screen. Here we go. Okay. Can you see the presentation?
Perfect.
Okay. There we go. Okay. Hi, I'm Karis, and for the past 6 weeks, I've been working with Chris and Spiros on a project of quantum chess. Quantum chess is a game to teach quantum, uses quantum principles to evolve a standard game of chess. For example, the quantum principle of superposition, most well known from Schrodinger's Dead and Alive Cat, is seen in the quantum chess move called the split move, where you have a target square like this king here, and then it splits into 2 other spaces, like from A1 to B1 and B2, and you can think of it being 50% in both squares. While there are other more complicated types of moves that made up of that use quantum principles such as entanglement or interference, what I plan to speak about today doesn't really, you don't need to understand those. You only really need to understand split moves. Now, I mentioned that quantum chess isn't just a game that uses quantum principles. It also is supposed to teach quantum principles. Quantum chess is a teaching tool, and this includes the code behind the game. Google developed a Python library called SRC, which the library is known as SRC, and in Google's words, it is an open source framework for programming quantum computers. It's specifically for writing, manipulating, and optimizing quantum circuits. And you can do things like writing a game of quantum chess on it. So Google provides guides and tutorials for this library, but none are quite so comprehensive as the quantum chess one, which was developed by Chris in collaboration with some engineers from Google. Unfortunately, as most things originally designed by experts, it was made for experts. And that's where I come in, someone kind of entirely new to the quantum scene. I went through the research documentation, a version of SRC that is made for research experiments for quantum chess, and to make sure it was understandable for someone who hasn't spent 15 years studying quantum computing. As with all journeys, I did prepare myself a little before going into this. I made sure I knew what a quantum computer was, and took a class hosted by QBraid, which is a company that is working to open up teaching quantum computing to high schoolers. Through my exploration, I gained a basic understanding of complex numbers, vectors, single and multi-qubit gates, as you can see exampled here, measurements, entanglements, Deutsch's algorithm, quantum computing 101, pretty much. And with that under my belt, I moved on to actually doing what I had been assigned to do for my internship. I went through the entire quantum chess research documentation, wrote a 10-page document, and then shared with Chris and Spiros what I had found. And while I could go into the joys of finding spelling or grammatical mistakes, I think it would be a much more interesting talk if I went to the thing I spent the most time on, which is data visualization. So in the quantum chess research documentation, there is a section called Concepts that explains how to use SRC by building a basic 3x3 quantum board and then playing out various moves and doing, teaching basic things like how to deal with noise, which I'll explain later, and, just kind of how to use SRC with a quantum chess lens. And one of the things you do in Concepts is you will program a series of moves and then run it over and over and over again, because on a quantum computer, you cannot see the internal state of the system. You can only tell what is going on from statistical measurements. So for example, this is a basic series of moves. You start with a king on A1, a queen on A3. You do a split move with the king to B1, B3. Then you do another split move with the king from B1 to C1, C3, and then this doesn't show the full series of moves that I'm going to continue talking about, but then the queen would move from A3 to B2, and then the king moves from C2 to C3. So this right here is some code from the concepts that goes through those moves. And as you can see down here, it prints out this lovely histogram of the number of times it appeared those spaces being occupied. So you can see that it sort of shows that you have the final state, a queen on b2 and then a king half on c1 and c3, but it's not exactly the most intuitive of demonstrations. And so I showed this to Chris and Spiros and was like, hey, can I try and, you know, make up some graphs to visualize this? And they were like, yeah, sure. So I, you know, went and using Seaborn, which is a Python data visualization library, I put together some graphs, and then I took them back to Chris and Spiros, and they said, can you make it 3D? And so, you know, I went and made it 3D. And so as you can see here, it is just a representation of that histogram, but it shows it a little more intuitively where you can see the board states and you can actually see that, oh, look, the queen is wholly here, and then you have the 250% of the king here and here. The colors act as a sort of heat map where you can see that the more red it is, the less percent chance it is of being there, and then the more green it is, the higher percent chance the piece is there. So, yeah, this is one example. Another example of where this data visualization can come in is with noise. So before I go into how you can use it to represent noise, I need to explain a bit about what noise is. So noise is, in quantum computing, the construction of qubits is very finicky, and so things can go wrong pretty easily. So this is just 3 types of noise, T1, decay / relaxation, where qubits, which are bits in quantum computers, go from an excited state, lose energy, and fall to the ground state 0. Readout / measurement errors, where you just accidentally measure the wrong thing, or control / coherent noise, where the device drifts out of calibration and your numbers go wonky. And so you end up with pretty messy data. So this is a really straightforward, another example of a series of moves. King on A1, A1 splits to B, B1, B2, then the king on B1 splits to C1, C2, and the one on B2 splits to C3 and B2. So again, the code representing that series of moves. And when you apply a circ noise model, you can see that it gets a lot more messy down here. You end up with having these stray random pieces that are showing up in places that they should not be. And so then what happens in the concepts is they then explain, oh, you can get rid of that and, you know, apply one way they talk about removing noise is saying, oh, we're just going to ignore all the pieces that shouldn't be there. It doesn't make sense they're there, and so it looks cleaner. But again, this representation between this mess right here and this right here sort of makes sense, but it isn't, again, the most intuitive. So that's where I came in and made this thing where you can see the noisy data down here, where it's kind of, you know, a lot more messy, and then once it's eliminated the noise, it looks a lot more clean cut. So my bar charts, while not the most my goal here was to represent the data, and I think that this way is much better than how they are done in the concepts, especially as this is supposed to be aimed at teaching people who aren't experts and who haven't a lot of experience with reading strings of numbers, and images are really helpful with that. One more thing I do want to show is in concepts. So this is a copy of the Google Colab that is from that I have modified with my code. Google Colab is essentially a it's like Jupyter Notebooks. You can do a mixture of coding and writing in it, and it's just a really good way of building tutorials. And as you can see, when I scroll to it, I have a lot of, you can start seeing. So I started with the 2D and then I went to the 3D. And, you know, it just goes through and it's actually representing all of these histograms. And I think one thing to end on that is probably a good one is this is, there's a really simple series of moves here where you have a king that is just moving across the board from, you know, A1 to A2 to A3 to B2, B3, and, or B2 and then C3, B3, C3, sorry. And because this is an example of coherent noise, which I mentioned, where the device is moving out of calibration, and so the king essentially leaks across the board and it's really messy, and it's very well shown here. And then once you've recalibrated it, you can see, oh no, where has that gone? Sorry, is this, oh, sorry. I think what's happened here is, there we go. So yeah, sometimes, no. That's a little distressing. There is a graph I have somewhere that this right here is entirely cleaned up. And for some reason I cannot find that, and I apologize because that shows it rather clearly. And yeah, so just going to move on. My hope is that I will have made, what I've made will help others understand the circ tutorials more easily, and that the data will no longer just be numbers, but graphical representations. And I want to say thanks to Spiros, Chris, and the SAR Caltech internship for giving me the opportunity to do this. Okay.
Thank you, Carrie. This is amazing. And don't worry about the bar graph. Like, you know,
yeah,
that's not an issue. You've shown way more than enough. Okay, we have questions, and you can stop presenting at this point.
Yeah, let me. Okay, stop share. There we go.
It's like Inception, you know.
Yeah.
Had you done data visualization before? I know you have some programming background, but was this new or something you already had in your toolbox?
So I'd had tiny bit of experience with Seaborn before, like a week of it in my by my teacher, and then I had about a week of it in my AP Computer Science Principles class. And then, yeah, so a lot of this was kind of new to me, and especially the 3D, I'd never done anything like that. So that was entirely figuring it out during this internship.
Very impressive in such a short amount of time to tackle that and be so successful.
Thank you.
Yeah, I have a question. So I noticed that when you reduce the noise of, or you just reduce the noise in one of your graphs, that's hard for me to like describe without seeing it. It's basically all the other like squares that rise up, they increased because you added what was removed from the, like, you removed the noise and added it onto the other you know, rectangles, right? So how did you know how much to add to each rectangle, like what the noise was supposed to be like moving towards?
So the data that was represented on them actually came from the concepts. So I was literally just taking the data from what it was outputting and graphing that. So how the noise changed was just a representation of what was changed in the histograms. If that helped answer your question.
In other words, there was error mitigation algorithms, right? That come with sampling and post-selection, where you throw away things that make no sense.
Yeah.
And then you renormalize, right? You're like, all right, these things were fake. if we put them back into the real, like, positions, zip, things kind of like get, increased to what they're supposed to be.
Okay, I see. Yeah, thank you.
We also have Rochelle with us, who is a proud alum of SRC. And she will be going to college in a month.
Yeah.
Rochelle, do you want to say hi?
Hello. Yeah, I'm going to college in less than a month. I'm pretty excited. I'm going to UC San Diego, so I'm moving soon.
Very impressive.
Yeah.
Congratulations.
Yeah, congrats.
Yeah.
And you'll be studying computer science. Is that what you're thinking?
Yeah.
Nice. What do you think of this cohort from this summer?
Sorry, I didn't quite hear you.
What did you think of the presentations and the work of these young geniuses?
I was so impressed. Like, everything was so amazing. Like, I was blown away with all the work you guys did in like 6 weeks. Like, I was like, oh my God, like top genius, you guys. And like, you guys didn't even know, like you were saying, oh, I was new, I had no idea. And I was like, okay, this looks too impressive for not knowing anything. You guys made yourself look professional. So I was blown away with your work. But,
yeah, I have to agree. Really great presentations too.
And Rochelle, you worked on aspects of this, related aspects, the last 2 summers, right? So this is your 3rd summer. Yeah. So, and some during the school year, I think. So you're a big part of moving this big engine forward.
That's right. Yeah, Rochelle actually worked with us way past last summer up until, I don't know, March of this year, and was working to help us implement a translation between C++ and Python, right, Chris? So you could, we could take the game and not have it run in the web browser directly, because there is networking, that needs to be done if you want students from around the world to have access to it, and so on and so forth. So
I have to ask, did you write about this in your college essays, I hope?
yeah, I definitely did. So I'm hoping they were impressed by that. I don't know.
It must have been, yeah.
So a quick question to all of the students who presented. Did you have any key takeaway from this, a meta level, like as far as like what the research even feels like? Because you were working on things that are, important to us, right? We didn't just create some random project and say like, okay, just do it so you learn something. This is, these are important things for both for teaching quantum concepts and also for developing like quantum chess as a full-on game. As I said earlier, right, the quantum chess AI, for example, is crucial to having at some point the ability to generate puzzles, right? And for Chris to not have to hard code the response to every possible thing somebody could do, as they're playing back and forth.
So the question was about like takeaways from just the program in general. Well, one thing that's more like programming related that I learned is I'm mostly used to like, sitting down, especially I took AP Comp Sci. And so for homework, you sit down and do the homework, and you kind of get it done pretty quickly. But for some of the stuff that I was writing like the past few weeks, it just wouldn't work. And I realized I had to either, go to bed or like go outside and just take some time off. And then afterwards I'd be able to find the solution, but just staring at the code doesn't really, yeah.
That's awesome. That is very much an important aspect of a research scientist's life, being able to turn off the brain, sometimes by sheer exhaustion, and you fall asleep and then you wake up refreshed and less upset about not having figured out the answer to an age-old problem within one evening. And yeah, I like that.
Sometimes it might take you a long time to get there. I remember one bug I was working on, it took me a month to figure it out, literally. And the solution came to me as I was laying in bed about to fall asleep one night. And it was just like light bulb. oh, that's the problem. And it was literally just a one-line fix, but took me an entire month to figure it out.
I think Dylan, were you gonna make a comment, Dylan? Did you raise your hand?
Yeah, I was just gonna say, like, make the problem as simple as possible. As I was saying about earlier, I wanted to do something like really complicated and really didn't have that much time to do it. So it's like, I should understand the use case and when it's going to be used for, and then make it as simple as possible and easy as possible for that use case. So like one of the main things was creating the puzzle, which I kind of like learned now in retrospect that I should have really like focused on searching quantum moves more than the non-quantum moves, because the whole point of the puzzles is to understand the quantum aspect. But that was hard to do, but also keeping it simple while still trying to apply for those quantum moves was something I kind of had to learn to do.
Yeah, this is wow. You're pretty smart, you know, and it's not just for your age, just in general. But yeah, these things take a lot of time for most people to realize that somehow simplicity requires like extreme depth, right? To reach a simple place where you can remove a bunch of assumptions, right? You know, and all these constraints that previous versions of things had. You need to just, as Robert and Chris also said, just be with it, right? Don't try to overcome it or to just win or whatever. Just, you know, steep yourself in it, and just being there, you start just thinking about some things just differently. For example, AlphaZero is a better chess player, right, than Stockfish. And what did it do? It said, like, I won't even try to force it to play like human chess, right? The best possible human chess. I will remove even that constraint, right? That it should think of the mid game in this way. It should evaluate these positions that way, right? Because of all the experience and wisdom we've had of thousands of years of like human chess players. Said, no, just play like a human being, you know, would play, but if they could live for thousands of years, and they could see all these great games, and then they started learning, right, almost from an evolutionary point of view, what the right ideas are. Just let it emerge from that and use computers to accelerate time. Karis, anything from you?
Yeah, one thing I really took away from it is just how much collaboration goes into projects like these. I sat in on a lot of meetings with the Google engineers and seeing them talk about how this project was unfolding. And it really is a lot of sharing of ideas and sharing of resources. And when you're sitting in a class with 10 other people and you're all on Zoom and you're not like working together, seeing it then actually in the real world, there's a lot more collaboration was, you know, a really cool experience.
Yeah, that's a really great point, because in school, it's almost, you're not allowed to collaborate. Sometimes it's called cheating, right? But in real life, it is the most important part. Like, this is how the greatest projects, like legendary things, happen, right? When you get to talk to other brains, and even if you're the world expert on something, just opening your mouth and bouncing ideas off of someone else and looking at their face, you know, as they're like, you're telling them stuff. I mean, it's happened actually with me and Chris, where he knows exactly, like, you know, the whole situation, and I'm completely lost because I haven't kept up with something, and he just tells me in mid-sentence, like, oh, I figured it out after a month, for example, or something like that sometimes, right? Or weeks. So that human element is extremely important, and to see also, and to have that respect and appreciation for other people's minds and how they do things. Like also with Robert and Dylan, I love the fact that towards the end you split, right? You're like, okay, I think I'm gonna go this way, and like you can go and try this other thing. And that is ironically exactly also what makes this AI so powerful. They split and try different things, and then they come back to report, like in this report right now, after your 6 weeks. And everyone gets to learn. It's kind of like Naruto and, you know, Kagebushi. So anyways, it's pretty powerful stuff, and I hope that you will all stick with this because we could use your help, and also you'll get to meet some pretty amazing people and network with them. And to close, I guess if Mitch or Rochelle, you have something you'd like to say, or Chris.
Sorry, I'll just say I'm so impressed with what you all achieved this summer, and then Rochelle over several summers and the school year, all contributing to this effort. And I think what was exciting today was hearing about like the life lessons you learned in terms of collaboration, partnerships, keeping something simple enough to achieve so you can have a success and move on to the next thing. That was very wise, Dylan, not to try to create something that would have been impossible to do in 6 weeks and then just kind of feel defeated at the end. You figured out a way to do something meaningful that was achievable. So learning all those lessons is probably the best lessons you all learned this summer, even more than the technical expertise and the other things you created and contributed to. So that's very rewarding for us who put the program together. I'm very grateful for Chris and Spiros for every year hosting students and helping them make these discoveries. So it's very wonderful and gratifying to all of us at Caltech that you're part of this.
Chris, any closing words?
I just wanted to say I really resonated with that simplifying of the problems thing, because this entire project started years ago as a final project for a class that I took for fun. And at the end of this course, we had 1 month to create something. And I sat down and I said, I'm going to create quantum chess. And after some looking, I thought, that's really way too complex. Let's simplify it way back. And so I created a quantum game that was a little 5x5 board with a single piece type, and the things hopped around using quantum mechanics. And then I met with Spiros, and over another year and a half or so, it turned into quantum chess again, and has just continued to become more and more complex from there. So really kind of taking things back to be very simple and starting from there, and then you can build on that and create that complexity over time, can really lead to some great results. So
yeah,
excellent. And Rochelle, as you go off to college, this is great advice for you as well. Whenever you feel overwhelmed, just remember, the foundations. If you have strong foundations, then you can build complex structures on top of them. So take the time to breathe, right? To sleep, to eat well, to work with others and collaborate, create friendships, and learn the foundations. Take the time, even if it takes sometimes longer than everyone else. That's not true. It's just nobody really knows what's happening early on in their undergraduate years. Take the time to appreciate, enjoy them, and then it will pay off.
And enjoy La Jolla. That's not too shabby.
Yeah, definitely. I just wanted to thank you guys for this opportunity. I really appreciate it because I'm going to take all these lessons, like never giving up, always go back at it, even though sometimes I was slow and there were ads and you guys would tell me, close the ads on the programs. But yeah, I'm definitely taking these mostly for computer science, and I'm definitely taking that. So I just wanted to tell you I appreciate you guys never giving up on me and going slow and teaching me one step by step, like holding my hand. But yeah, I'm definitely taking that.
That's awesome.
Thank you.
Well, thank you. Thank you all, and good luck with school, which started yesterday for many of you. Hopefully you feel empowered that you're already working with some of the top people in the world, right, on some of the things you may want to study even later on in life, and that they see you with respect, right, and are very impressed. So, all right, let's call it a week. Enjoy your weekend, okay, and have a great school year.
Thank you. Bye, everybody.
Thank you. Bye.
Thank you. Bye.
thanks.